Alright, this will be one of the final videos we have over our initial probability unit, and this video is on independence and probability. And I have the picture of the American flag here because as a country we are considered to be independent, right? We broke away from England after the Revolutionary War to show our independence. We signed the Declaration of Independence to show that we did not depend upon the country of England anymore. We were all by ourselves. So that's kind of the same idea when we're talking about independence with probability. So what does it mean for two events to be independent? Well, here we go. Two events, A and B, are said to be independent if each event, of each other, if the outcome of one event does not impact the outcome of another event. So it's actually got a lot of common sense. Two events are independent if the outcome of one event has no impact on the outcome of the other event. They're both independent of each other. Now we actually have a way to prove that two events are independent. And we have to use this formula. If we could prove that the probability of A equals the probability of A on the condition of B, or if we can prove that these are equal probabilities, then it shows that B doesn't impact A. Now some kids get confused by that, so let me explain. On this side over here, I'm finding the probability of A. Easy, okay. On this side over here, I'm finding the probability of A as well, but on the condition that B has already occurred. If these two probabilities are the same, then it just goes to show that my condition of B already occurring did not change the probability of A. For example, if the probability of A is 0.45 and the probability of A on the condition of B is 0.45, then that means there's a 45% chance of A occurring, and there's also a 45% chance of A occurring if B occurred, showing that B occurring or not occurring didn't change the probability of A at all. Okay? Now, let me switch that up real quick here. Let me just change these numbers around so you can understand this. If the probability that A occurs is 0.45, but the probability of A occurring if B occurs is 0.23. Well, they're not equal. That means they're not independent. What this shows that the probability of A occurring is 45%. Easy. However, if B occurs, the probability of A drops to 23%. What that tells me is that B impacted A. B played a part in lowering the probability of A. So if B is impacting A, then obviously they're not independent of each other. Alright? So understand that this formula shows that whether B is a given or not does not change the probability of A. So if we come up with an equal statement, then we are independent. If it's not equal, then they're not independent. Now, just so you're aware, I could switch around the variables. I could switch the B's. So in this case, I'd be saying, hey, what's the probability of B? Does that equal the probability of B given A? So I could show either way. It technically does not matter which way you show it. If you show it either way, just make sure that you realize that if they're equal, you're independent. If they're not independent. Okay? So let's understand this with a really, really simple example. So here's a two-way table. We got male, female, right-handed, left-handed, or ambidextrous. Okay? So two variables. Which hand do you use, and are you male or female? So the question is gender independent of the dominant hand? In other words, does being male increase or decrease my chances of being left-handed? Now I'm choosing to focus on male and left-handed, and I'm going to show you how I could choose to focus on other variables and I would still get the same answer. So basically, I want to know what's the probability that I'm left-handed. And I want to see, does that equal the probability of me being left-handed given I'm a male? And what this is going to show me, does being a male change my chance of being left-handed? Well, what's the chance that somebody at random is left-handed? Well, if I look at the chart, 6 people are left-handed out of 30. Very, very easy. I could grab my calculator if I need to. 6 out of 30 is 0.2. So there's a 20% chance that a left-handed person is selected. All right, well, let's do this one. If I'm a male, given that I'm a male, now remember, this changes my denominator because I'm only allowed to look at the 16 males. If I know I'm a male, that reduces it to down 16, right? I'm only allowed to look at the 16 males, and of those 16 males, 4 are left-handed. So 4 out of 16 is 25%. So what I just found out is that these are not independent. Okay? These two variables are not independent because they're obviously not equal. What this actually shows me is that if I am a male, I'm slightly more likely to be left-handed. If I'm a male, I'm slightly more likely to be left-handed. Interesting. All right, I could switch this around and choose some other variables just to show you that it still works. For example, maybe you want to look at females and right-handed. So I'm going to say, what's the probability that I am right-handed? And I want to see what's the probability that I'm right-handed on the condition that I am a female. I want to know, does me being a female change the probability of me being right-handed? Well, on the left-hand side, all I care about is being right-handed. 23 people are right-handed out of, whoop, sorry about that, a little typo there, 23 people out of 30. 23 people out of 30. So 23 out of 30 is 0.7667, about a 77% chance of being right-handed. Okay, on the other side here, I'm only allowed to look at females. The condition is I must be a female. So of the 14 females, 12 are right-handed. So again, notice that's conditional because I'm only allowed to look at the 14 females. That's my condition, 12 of which are right-handed. So 12 divided by 14 is 0.8571. Once again, not independent. All right, because they're not equal. What does this show me? This shows me that if I'm a female, I'm actually slightly more likely to be right-handed. So based on this survey, females are more likely to be right-handed, males are more likely to be left-handed. This proves that they are not independent. Your gender plays a part on you being left or right-handed. So again, this is how easy independence can be with this formula. Okay? All right, let's take a look at another example here, just to make you really convinced how easy this is. Another chart here, actually we think we looked at one like this in class. We have gender and then driving a sports car, an SUV. Is there any type of relationship, is there any type of association between the car I drive and the gender I have? So remember, if I'm talking about an association, I'm talking about independence. Does A affect B? Are A and B associated? Does gender and what kind of car I drive associate? So again, you could pick any of these. I'm going to pick male and I'm going to pick sports car. So I want to know, does the probability of me driving a sports car, is that equal to the probability of me driving a sports car given I am a sports car, given I am a male? Does me being a male impact the chance of me driving a sports car? Well, what's the probability that somebody drives a sports car? All I care about on the left-hand side here is sports car. 84 out of the 240 people drive a sports car. 84 out of 240 is 35%. So 35% or 0.35% of people have a sports car. However, let's see if this is equal. I'm questioning this. If I'm a male, that changes my denominator. I'm only allowed to look at the 60 males. Amongst the males, 39 people have a sports car. 39 out of 60 is 65%, 0.65. So, wow, not independent. Clearly, there is an association. Something about being a male increases my chance of having a sports car. So when you're asked about independence, usually you have to do a little bit more than just show the work, right? So you want to actually write out a nice solution here. So you would write out, after you do this work and clearly identify the fact that 35% does not equal 65%, you'd write something like, the two variables, gender and car, are not independent. For example, if you are a male, you are more likely to drive a sports car than if you're not a male. 35% chance to drive a sports car. If you're a male, it increases to 65%. So clearly gender plays a part on what type of car you drive. And that means that they are not independent, which means that there is an association. So keep in mind that not independent equals an association. Right? If two variables are not independent, then that means that they are associated. One impacts the other. Very, very simple. Okay, here, so we went through two examples, and hopefully that was very, very easy. All right, now let's make a connection to something we learned earlier. All right, in the last video of our conditional probability, we learned that the probability of A and B is equal to the probability of A times the probability of B on the condition of A. And I was extremely animate about the fact that if you want to multiply two probabilities together, you better believe that you're thinking conditional. I can't just multiply two things together without consequence. You must make sure that the two variables are connected, right? I got to make sure that A times B, but I got to make sure that B is on the condition that A occurred. Well, think about this. We just talked about independent. So if A and B are independent, then that means that the probability of B equals the probability of B given A. But this is only true if independent. Well, if that's true, I could replace the probability of B on the condition of A with just the probability of B. So I get a new formula that the probability of A and B equals the probability of A times the probability of B. But I cannot stress this enough. This is only true if you are independent. If you are independent, if A and B have nothing to do with each other, you are allowed to multiply their probabilities together to get A and B. But the moment there's some type of association, the moment that A changes the likelihood of B occurring or B changes the likelihood of A occurring, you're not allowed to multiply without thinking. So to understand this with some simple examples, I made up two really easy examples. All right. First off, you're going to roll a die and you're going to flip a coin. These are clearly independent events, right? Why are they independent? Because the outcome of me rolling a die will have absolutely no impact on the flip of that coin. If I roll a 6, that's not going to make a head any more or less likely than getting a tail. Let me just kind of give you an example down here. The probability of rolling a 4 is equal to the probability of 4 even if I get a tail. If I get a tail here, that's not going to change the probability of me rolling a 4. The probability I roll a 4 is 1/6. The probability I roll a 4, even if I throw a tail, is still 1/6. It doesn't change it. So in this case, because they're independent, I can answer this question. What's the probability that I roll a 4 and then get a tail? Well, since they're independent, I'm allowed to multiply. The probability of rolling a 4 is 1/6 times the probability of getting a tail is 1/2. That means the probability of me taking a die, rolling it and getting a 4, and then flipping a coin and getting a tail is 1 out of 12. Very simple. Why was I allowed to multiply those two things without thinking conditionally? Because they were independent events. All right, now let's come over to the second example. Second example is I got a jar with 3 red marbles, 5 blue marbles, and 2 green marbles. What's the probability that I pull out 2 marbles? I'm pulling out 2 marbles and I get a red and a blue one. Now this is non-replacement, which means I'm going to pull out a marble and keep it. I'm not putting it back. And then I'm going to pull out a second marble and keep it. So this time they are not independent, right? Because if I pull out a red one, let's say that's event A. When I reach in, the chance of me getting a blue one just changed. Why? Because there's 1 less marble in that jar. So these two events, red and blue, first pull, second pull, are not independent because I'm keeping that first marble I pull out. This doesn't make probability hard. It just makes probability something you have to think about. So what's the probability I reach in and get a red marble? 3 out of 10 marbles are red. Okay, and then I want to get a blue marble. Well, there are 5 blue marbles in the jar, but only 9 total marbles. So all I did was think about it. It wasn't very difficult. I just had to think about the fact that when I reached in that second time, the probability changed because of what happened the first time. So here I get 15 over 90, and 15 over 90 would reduce to 1/6 or 0.1667. So you get the idea. Two different problems. The one on the left is independent. The one on the right is not independent. But I could do them both with multiplication as long as I use my brain. Please use your brain. Okay, another example here I want to talk about was dealing with the Space Shuttle Challenger. Now, if you guys all recall, the Space Shuttle Challenger was a space shuttle that blew up upon its departure from the launch pad. Now, they were pretty confident that they weren't going to have any issues, and here's why. On the thrusters, there were 2 thrusters on each side of the spaceship, right? Spaceship was in the middle. These thrusters had what's called O-rings. These O-rings were these rings that went around that linked the fuel tanks together, okay? They were round, rubber kind of rings that went all the way around the fuel tank. Well, they believed, they knew that the probability that an O-ring works, right, was 0.97. I really wrote that pretty messy. The probability that the O-ring works was 0.97. So they were pretty confident that nothing was going to go wrong. But they didn't think about independence. See, the idea here was that there were 6 O-rings all going up into space at the same time. And they needed all 6 to work. So what's the probability that all 6 work? Well, we have to assume that they were independent of each other, meaning that if this one right here broke, it wasn't going to impact this one or this one. They were independent of each other. As long as that was true, here's what happens. The probability that all 6 work means that we need the first one to work, and multiply the second one to work, and multiply the third one to work, and the fourth one, and the fifth one, and the sixth one. This is actually pretty easy to do on my calculator. It would be 0.97 to the 6th. I need all 6 O-rings to work. Well, 0.97 raised to the 6th is 0.8329. So that's the problem. Even though there was a 97% chance that an O-ring works, sounds really good, sounds like very little room for error. When you put all 6 O-rings together and they're working independently, now you have an 83% chance that they all work. So no wonder there was a large percent chance, right? The chance that they were not going to work was the opposite of that, right? The chance that at least one O-ring doesn't work would be 1 minus that probability. So there was about a 16, almost 17% chance that there was going to be failure. So it's sad, but that's basically what happened on the Spaceship Challengers. An O-ring broke and the space shuttle crashed. But hopefully you understand the idea of probability here. Now, one statement I want you to understand is that if 2 events are mutually exclusive, they cannot be independent. This is a pretty important statement. I see it on a lot of tests. If 2 events are mutually exclusive, they cannot be independent. Let me explain why. Mutually exclusive means that your 2 events have no overlap. For example, getting an A in this class and getting a B in this class. The probability of you getting an A and a B is equal to 0. Now, why does this mean they cannot be independent? Because the moment that you get an A on your report card, the chance of you getting a B drops to 0, meaning that the outcome of A affected the outcome of B. And if you have 2 completely separate mutually exclusive events, they cannot be independent. The outcome of one will always affect the outcome of the other. Now here's the issue. If they are not mutually exclusive, they're connected, they're overlapped, sometimes you're independent and sometimes you're not. That's why when you have 2 overlapping events, you have to be so careful if you're going to multiply or not, because you're only allowed to multiply if you know that they are independent. If you are connected, if you are overlapped, you might be independent, you might not be. It all depends on the problem. So the one thing we know for sure, without a shadow of a doubt, is only if you are mutually exclusive, we know that you cannot be independent. Okay? One last problem to go, and this video is done. Okay, I see this problem all the time on the AP test. If the probability of A is 0.35 and the probability of B is 0.78, find the probability of A or B under 2 scenarios here. The first scenario is A and B are mutually exclusive. Okay, you just got to remember what this means. Mutually exclusive means that A and B is equal to 0. There's no overlap. So I'm going to go ahead and use the formula for the probability of A or B. The formula for the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. So let me start filling things in. The probability of A is 0.35. Awesome. Plus the probability of B is 0.78. Awesome. Minus the probability of A and B. Well, if I'm mutually exclusive, it's a big fat 0. Don't even have to worry about it. That means that the probability of A or B would be 0.35 plus 0.78. All you got to do is add them together. 0.35 plus 0.78. And I just realized I chose a really bad example for this because that's going to add up to a probability over 1. So I really apologize for this, but I'm going to have to change the probability of A to something like 0.06. I made a big blunder there. I'm really, really sorry. All right, let's switch this around real quick. The probability of A is 0.06. Ignore what I said earlier. So now 0.06 plus 0.78 would be 0.84. Okay, it doesn't take away from the fact that if you're mutually exclusive, the probability of A and B is a big fat 0. All right, now let's do the whole problem all over again. Let's find the probability of A or B if A and B are independent. Well, that means that the probability of A plus the probability of B minus the probability of A and B. Okay, well, again, still using that same addition formula. The probability of A is 0.06 plus the probability of B is 0.78. This time, well, independent means you could be mutually exclusive, you could not be, so I don't know if this is 0. But wait a minute, remember, if you're independent, the probability of A and B is equal to the probability of A times the probability of B. Again, this is only true. This statement right here is only true if you're independent. Well, it says they're independent, so to figure out A and B, I'm just going to take 0.06 times 0.78, and I get 0.0468. Okay? So now to find the probability of A or B, I'm going to take A, 0.06, plus B, 0.78, minus the 0.0468, and I get 0.7932. So, understand that if I didn't know they were mutually exclusive, if I were like, well, they might be mutually exclusive, they might not, I don't know, this problem would be unsolvable because I wouldn't know the and. Well, if I didn't know they were independent, they might be independent, they might not be, I don't know, this problem would once again be unsolvable because I wouldn't be able to figure out the and. Because remember, you're only allowed to multiply A times B if you know they're independent. So under these two scenarios, the problem is very easy to solve. Mutually exclusive, this back part here is a big fat 0. Independent, this back part here is simply A times B. Any other scenario where I don't know about mutually exclusive or independent, problem can't be done. Alright, so that's it for the independence video. Hopefully it was not too painless. If you're still a little bit confused on it, we're going to do tons of examples in class to make sure you guys understand.